The date is September 26th, 1918, the hour 5:30 in the morning. Along a 24-mile stretch of the Western Front, 2,775 American guns erupt simultaneously. The largest artillery bombardment in American history, before or since tears the pre-dawn darkness into ribbons of fire. The earth shakes. Men miles from the front feel the tremor in their bones. But here is what the German defenders in their fortified positions do not understand. Not yet, not until the shells begin falling with terrible accuracy on positions they believed hidden, on batteries that had never fired a shot to reveal themselves, on command posts and supply dumps and communication trenches that no American gun had ever ranged upon. There had been no warning shots, no telltale registration fire walking slowly toward their lines over previous days. The Americans had simply calculated and fired and hit. 18 months earlier, this would have been impossible. 18 months earlier, the United States Army possessed fewer than 600 modern artillery pieces. Its doctrine was a relic of the 19th century. Its officers had never witnessed indirect fire at scale, had never coordinated a creeping barrage, had never heard of sound ranging or predicted fire or meteorological corrections. The American army that declared war in April 1917 ranked 17th in the world, behind Portugal. And yet here, in the Meuse-Argonne, American artillerists were executing techniques that had taken European armies 4 years of bloodshed to develop, and in some cases, executing them better. How does an army transform itself so completely, so rapidly? How do amateurs become annihilators? This is that story. To understand the magnitude of what American artillery achieved by 1918, we must first confront the depths from which it climbed. When Congress declared war on Germany on April 6, 1917, the United States Army was not merely unprepared. It was, by the standards of industrialized warfare, barely an army at all. The entire regular force numbered roughly 127,000 men, fewer than the casualties suffered by France in single battles. The National Guard added another 180,000, mostly untrained for modern combat. But the artillery situation was particularly dire. The United States possessed 544 modern field guns. France, by comparison, was producing that many every week. The standard American piece was the M1902 3-inch gun, a respectable weapon for the Philippine insurrection, but hopelessly outclassed by the monsters of the Western Front. The Army owned exactly 0 heavy howitzers of the type that had become the dominant voice of European battlefields. More troubling than the equipment shortage was the doctrine that governed its use. American artillery thinking had essentially frozen in 1905. Officers trained at Fort Sill learned techniques that Napoleon would have recognized: direct fire, open sights, guns positioned where crews could see their targets. The concept of indirect fire, lobbing shells over hills and forests at enemies miles away, guided by observers and mathematics rather than line of sight, existed in American manuals, but practical experience was almost non-existent. No American artillery officer had ever coordinated a bombardment involving more than a few dozen guns. None had experienced the synchronized rolling barrage that had become essential to infantry survival on the Western Front. None truly understood that artillery was no longer a supporting arm. It had become the main event, the terrible engine around which all other military operations now revolved. The statistics were stark and unforgiving. By 1917, artillery fire caused between 60 and 70% of all casualties on the Western Front. Machine guns, rifles, bayonets, poison gas, all the horrors that dominated public imagination, together accounted for less than a third. The war would be won or lost by the guns. General John J. Pershing understood this when he arrived in France in June 1917. What he found there deepened his concern into something approaching alarm. The French and British had learned their artillery lessons in blood. The Somme, Verdun, Pas-Yandele, each catastrophe had taught brutal truths about the relationship between artillery preparation and infantry survival. A barrage too short left machine gun nests intact to slaughter advancing troops. A barrage too long churned the ground into impassable mud and gave defenders time to bring up reserves. a barrage poorly synchronized with infantry movement, either stranded soldiers in no man's land or dropped shells on friendly troops. The Europeans had spent 3 years dying to learn these lessons. Pershing had perhaps 18 months to absorb them before his army would be expected to fight. The American expeditionary forces faced a choice. They could spend years rebuilding American artillery from scratch, designing new guns, constructing new factories, training new crews in American methods. Or they could borrow, they could learn. They could take what the French and British had purchased at such terrible cost and make it their own. Pershing chose the latter. He had no alternative. In the summer of 1917, American artillery officers began arriving at French training schools in a state of profound humility. These were not ignorant men. Many held engineering degrees from MIT, Yale, and other technical universities. But they were about to discover how much they did not know. The French artillery school at Fontainebleau became their first classroom. Here, American officers encountered the Soixante-Quinze, the legendary French 75mm field gun, a weapon the French regarded with something approaching religious veneration. The 75 had saved France at the Marne in 1914. It could fire 15 rounds per minute with remarkable accuracy. It would become the standard American field piece for the duration of the war, and American gunners would learn to love it as the French did. But the gun itself was merely the beginning. What the French taught was a philosophy of artillery employment that bore little resemblance to anything in American experience. The concept of the rolling barrage, the creeping barrage, was central. Imagine a curtain of explosions advancing across the battlefield at a precisely calculated rate, perhaps 100 meters every 4 minutes. Infantry follows immediately behind this curtain, close enough to feel the concussion, close enough that fragments sometimes fall among them. The barrage suppresses enemy defenders, keeps their heads down, prevents them from manning their machine guns until the infantry is upon them. The mathematics must be perfect, too fast, and the infantry cannot keep up. The barrage races ahead, the defenders emerge, the infantry dies, too slow, and the infantry walks into their own shells. The synchronization of watches, the calculation of rates, the coordination between artillery and infantry commanders, all of this was new to American officers in 1917. But the French taught something more profound still, the concept of predicted fire. In the early years of the war, artillery targeted enemy positions through registration, firing ranging shots, observing where they fell, adjusting aim until shells landed on target. This worked, but it carried a fatal flaw. Registration fire announced your intentions. The enemy knew exactly where you planned to attack. They could reinforce, dig deeper, prepare counterstrokes. The French had begun developing methods to eliminate registration entirely, using precise surveys, detailed maps, careful calibration of individual guns, and mathematical corrections for weather conditions. A skilled artillery unit could theoretically calculate a firing solution so accurate that the first shells would land on target. No warning, no registration, just sudden, accurate death. The Americans absorbed this knowledge, then traveled north to learn from the British as well. The Royal Artillery had developed complementary techniques born from their own bitter education. Sound ranging used arrays of microphones to detect the acoustic signature of enemy guns firing, triangulating their positions to within 50 meters. Flash spotting employed observers with specialized instruments to locate enemy batteries by the brief flicker of their muzzle flashes. Together, these methods could find hidden guns that aerial observation had missed. The British also emphasized meteorological science. A shell's flight is affected by air temperature, humidity, barometric pressure, wind speed, and direction at various altitudes. A firing solution calculated for standard conditions might miss by hundreds of meters in actual field conditions. The British had established elaborate networks of weather stations, sending regular meteorological telegrams to artillery units, so gunners could correct their calculations. American officers filled notebooks with these techniques. They asked endless questions, they practiced calculations late into the night, and they began to see the outline of something transformative. Not simply new techniques, but an entirely new way of thinking about artillery. The old model was artillery as craft, as art, the experienced gunner with the practiced eye who could sense where his shells would fall. The new model was artillery as engineering, as applied science, the systematic collection of data, the rigorous mathematical analysis, the reduction of uncertainty through measurement and calculation. This was a revolution the Americans were uniquely positioned to embrace. The United States in 1917 was the world's foremost industrial and engineering power. American factories had pioneered mass production, standardization, the systematic application of scientific management. American engineers had built the Panama Canal, strung telegraph wires across a continent, created the modern corporation. This culture of systematic problem-solving would prove decisive in transforming American artillery. In France, the AEF established its own artillery school at Saumur, where French and British methods could be taught, adapted, and refined for American use. But the real innovation happened in the specialized technical sections that American commanders created to support their gunners. 8 sound-ranging sections were established, each equipped with sensitive microphones, precision timing equipment, and trained mathematicians who could convert acoustic data into firing coordinates. Flash spotting sections complemented them, their observers scanning the horizon through specialized instruments. Survey teams fanned out across American sectors, creating accurate maps that were essential for predicted fire. Without knowing precisely where your own guns stood and precisely where the target lay, no amount of mathematical sophistication could produce accurate fire. American surveyors, many of them trained civil engineers, established baseline networks, triangulated positions, created the geometric foundation upon which precision shooting depended. Meteorological sections gathered weather data with unprecedented frequency. In some sectors, American units received updated atmospheric corrections every 4 hours, far more often than their French or British allies. Every new telegram allowed gunners to refine their calculations to account for the ever-shifting conditions of the atmosphere. And then there were the calibration procedures. Every gun is slightly different. Manufacturing tolerances where patterns, variations in barrel length and bore diameter. These differences mean that 2 guns of identical type fed identical ammunition will not shoot identically. The French had developed methods for measuring these variations and correcting for them. The Americans systematized these methods with characteristic thoroughness. Guns were calibrated. Ammunition lots were tested to establish their precise ballistic characteristics. Data was recorded, analyzed, distributed. A gunner preparing a firing solution could consult tables telling him exactly how his specific gun, firing this specific batch of ammunition, would perform under these specific atmospheric conditions. The result was predicted fire of remarkable accuracy. But the Americans added something else: speed. The Europeans had developed these techniques over years, building organizations that sometimes moved with bureaucratic deliberation. American officers, trained in a culture that valued efficiency, sought to accelerate every process. Survey teams developed faster methods for establishing positions. Sound-ranging sections reduced the time from detecting an enemy gun to producing its coordinates. Firing solutions that might take European units hours could sometimes be calculated by American crews in minutes. This speed would prove critical in the mobile warfare of 1918, when positions changed too rapidly for leisurely calculation. Not everyone embraced the transformation. Older American officers trained in the pre-war army sometimes resisted the new methods. They believed in what they called the eye of the gunner, the intuition of experienced artillerists who could sense where shells would fall. They distrusted the young engineers with their slide rules and their firing tables, their insistence that mathematics could replace instinct. These officers were not fools. Artillery gunnery does involve elements of judgment that cannot be fully captured in equations, but the weight of evidence was against them. In the conditions of the Western Front, with targets invisible beyond the horizon, with dozens or hundreds of guns requiring coordination, scientific methods consistently outperformed intuition. The Old Guard fought rearguard actions throughout 1917 and into 1918. But by the summer of 1918, when American forces began offensive operations in earnest, the transformation was largely complete. American artillery had become a scientific enterprise. Saint-Mihiel, September 12, 1918. This salient, A bulge in the German lines that had persisted since 1914 would be the first major American offensive of the war. For Pershing, it was vindication of his insistence that American forces fight as an independent army, rather than being parceled out to reinforce French and British units. For American artillery, it was the first great test. More than 3,000 guns supported the operation. The vast majority French-made 75s and 155s, but crewed by Americans, directed by Americans, employing methods that Americans had refined and systematized. The bombardment began at 1 a.m., 4 hours before the infantry assault. The fire plan was intricate. Counter-battery fire sought to neutralize German artillery before it could disrupt the advance. Destruction fire targeted known strongpoints, machine gun nests, command posts, and then the rolling barrage, advancing at precisely calculated intervals, 100 meters every 4 minutes, the infantry following so close they could smell the cordite. Saint-Mihiel was a success. Within 36 hours, the salient was eliminated. 15,000 German prisoners taken, 250 guns captured. American casualties were moderate by Western Front standards. But critics noted that the Germans had already been planning to evacuate the salient. The defenders were second-line troops, their positions not fully developed. Saint-Mihiel proved that American artillery could execute complex fire plans, but against weakened opposition. The true test still lay ahead. It came 2 weeks later, in the Meuse-Argonne. This offensive, the largest operation in American military history, would ultimately involve 1.2 million American troops fighting across 47 days of continuous battle. The terrain was nightmarish: dense forests, deep ravines, fortified heights that the Germans had spent 4 years preparing. The Kriemhilde Stellung, the main German defensive line, was a masterwork of military engineering. American artillery faced challenges that dwarfed Saint-Mihiel. The front was broader. The defenses were deeper. The terrain channeled movement into killing grounds that German gunners had pre-registered with terrible precision. Logistics strained and sometimes broke under the weight of ammunition requirements. The first days were costly. Infantry advanced into positions that artillery had failed to adequately suppress. German counter-battery fire proved more effective than expected, silencing American guns at critical moments. The lost battalion elements of the 77th Division cut off in the Argonne Forest became a symbol of the operation's difficulties, and artillery's desperate attempts to support them without accurate knowledge of their position illustrated the fog of war that no amount of science could fully dispel. But something remarkable happened. As the battle continued, American artillery improved. Not over months, but over days. Sound-ranging sections became more efficient at locating German batteries. Counter-battery fire grew more accurate. The coordination between artillery and infantry tightened as officers learned from each engagement. Fire plans for the assault on the Kriemhilde Stellung in mid-October showed sophistication that would have been impossible 6 weeks earlier. German accounts from the Meuse-Argonne increasingly expressed surprise and respect for American artillery. Defenders noted that American fire arrived without warning on positions they believed concealed. Battery commanders reported losing guns to counter-battery fire before they could effectively engage. By November, when the final American offensives shattered the remaining German defensive lines, American artillery had achieved a level of effectiveness that matched or exceeded their European teachers. In 18 months, they had compressed a learning curve that had taken the French and British 4 years of catastrophe to climb. To understand what American artillery achieved, we must understand the technical foundation upon which their success rested. Consider the problem facing a battery commander in 1918. His guns are positioned in a ravine, invisible to the enemy, but also invisible to the target. His objective is a German machine gun nest 2 miles away, concealed in a ruined farmhouse. He cannot see it. His guns have never fired at it. Yet he must hit it accurately with his first shells, because registration fire would alert the Germans to reinforce or relocate. The solution requires the synthesis of multiple data streams. First, survey data. The battery's position must be known with precision, not just the approximate location on a map, but the exact coordinates established by triangulation from known reference points. The target's position must be equally precise, derived from aerial photographs, sound-ranging data, intelligence reports, or observer coordinates. Second, weapon data. The specific gun to be fired has been calibrated. Its muzzle velocity has been measured. How fast shells leave the barrel, variations from the standard model are recorded. The ammunition lot has been tested to establish its ballistic characteristics. Third, meteorological data. Temperature at the battery position and at various altitudes, wind speed and direction at multiple levels. Shells arc through different air layers during their flight. Barometric pressure, humidity. Each factor affects the shell's trajectory. Fourth, the firing tables. These are books of ballistic calculations, showing where a standard shell fired at a given elevation will land under standard conditions. The gunner uses these tables as a starting point, then applies corrections for all the non-standard factors, his gun's particular characteristics, the ammunition's variation, the weather conditions. The calculation might proceed as follows. The range to target is 3,500 meters. The firing table shows that a standard gun under standard conditions requires an elevation of 285 mils to achieve this range. But this gun shoots slightly fast, add 3 mils. Today's temperature is below standard, subtract 5 mils. A headwind will slow the shell, add 2 mils, and so on, correction upon correction, until a final firing solution emerges. Done correctly, the shell will land within lethal radius of the target. Done across an entire battery, an entire battalion, an entire army corps, the cumulative effect is devastating precision. The Americans did not invent this system. The French and British developed its components, but American artillery systematized it with unprecedented thoroughness, accelerated its processes, and trained thousands of officers and enlisted men to execute it under combat conditions. The philosophical implications were profound. War had become, in some fundamental sense, an engineering problem. The chaos of battle could be partially tamed through measurement, calculation, and systematic procedure. A young lieutenant with accurate data and a slide rule could outperform a veteran artillerist relying on instinct. This was deeply democratic. In an unexpected way, excellence in artillery became achievable through training and method rather than depending on rare individual genius. The American approach could be scaled, could transform thousands of ordinary men into effective practitioners of scientific warfare. It was also deeply industrial. The same mindset that had created assembly lines and standardized parts now created standardized procedures for destruction. War had become a manufacturing process, and the Americans excelled at manufacturing. The armistice of November 11, 1918, ended the killing but not the thinking about what American artillery had achieved. In the years immediately following the war, the United States Army conducted extensive studies of artillery performance. The Field Artillery School at Fort Sill became a center for refining and preserving the methods developed in France. Officers who had mastered predicted fire and counter-battery techniques returned to teach their knowledge to a new generation. The institutional memory proved robust, at least initially. American artillery doctrine in the 1920s incorporated the scientific methods learned in 1917 to 1918. Training emphasized the technical skills, survey, meteorology, calibration, calculation, that had proven decisive, but institutional memory is fragile. The interwar years brought savage budget cuts. Training exercises grew rare. Equipment aged without replacement. The officers who had fought in France retired or died. By the late 1930s, American artillery had lost much of its edge. The Renaissance came, as it often does, through crisis. When the United States entered World War II, artillery commanders could draw on doctrine that had never been fully forgotten, even if practical skills had atrophied. The relearning came faster the second time. By 1944, American artillery in Europe had achieved a level of effectiveness that German commanders consistently identified as the most dangerous element of American military power. Field Marshal Erwin Rommel, who faced American guns in North Africa and Normandy, reportedly called American artillery the best in the world. German veterans of the Eastern Front, accustomed to the overwhelming numbers of Soviet artillery, were often more frightened by the precision of American fire. Soviet guns saturated areas. American guns hit specific targets. The techniques evolved. Time-on-target missions, where multiple batteries calculated their fires so that shells from different positions arrived simultaneously, became an American specialty. Forward observers with radios brought fire on targets within minutes of request. The integration of air observation with ground-based calculation reached new levels of sophistication. All of this built upon foundations laid in 1917 to 1918. The lineage extends further still. The precision-guided munitions of contemporary warfare, GPS-guided shells, laser-designated bombs, missiles that strike within meters of their aim points, are technological descendants of the mathematical revolution that American artillerists embraced a century ago. The fundamental insight remains unchanged. Accuracy is a product of data, calculation, and systematic method. Yet the human dimension of this story has largely been forgotten. Artillery lacks the romance of aviation, the visceral drama of infantry combat, the strategic sweep of naval warfare. The men who served the guns, who calculated the firing solutions, who operated the sound-ranging equipment and surveyed the positions, these men rarely became heroes of popular memory. Their work was technical, mathematical, unglamorous. They were engineers of destruction, and their anonymity is perhaps appropriate. The revolution they created was not about individual genius, but about collective method. No single figure embodies American artillery's transformation, the way Rickenbacker embodies American aviation, or York embodies American infantry. The revolution was systematic, institutional, organizational qualities that make for effective warfare but poor mythology. Return with me now to the Meuse-Argonne, September 26, 1918. The guns are firing, 2,775 of them, their thunder rolling across the hills of eastern France. In dugouts and trenches, German soldiers press themselves against the earth, waiting for the storm to pass, not yet understanding that this storm has been aimed with mathematical precision. We know now what we could not have known then, that this bombardment represents a transformation. That the artillerists serving these guns have, in barely 18 months, mastered techniques that their enemies developed over 4 years of industrial slaughter. That the calculations behind each shell reflect a synthesis of French rigor, British innovation, and American systematization. We know that these men are the pioneers of something larger than themselves, that the precision they achieved with slide rules and firing tables would eventually evolve into guided munitions and digital targeting systems, that the marriage of American engineering culture to the demands of modern warfare, first consummated in these fields, would shape the conduct of every American conflict for the next century and beyond. The doughboys who served those guns are gone now, every one of them. The last American veteran of the First World War died in 2011, carrying with him memories that no archive can fully preserve. The shell casings have rusted away. The gun positions have returned to farmland and forest, but the transformation they embodied persists. Every time an American artillery shell strikes its target with precision, it validates the insights first applied in earnest on the Western Front. Every fire direction center, every meteorological correction, every systematic calibration procedure traces its lineage to the desperate learning of 1917 to 1918. The American soldiers who crossed the Atlantic that year believed they were going to win a war. They did that. But they also did something they could not have anticipated. They established American artillery as the most effective precision force in the world, a reputation it has never relinquished. History remembers the doughboys who went over the top, the pilots who dueled in the skies, the generals who planned the campaigns. History too rarely remembers the men who calculated the angles, measured the weather, surveyed the positions, and sent their shells across the horizon to fall, with mathematical precision, upon targets they could not see. This has been their story. From amateurs to annihilators, in 18 months, through rigor and method and the systematic application of science to the ancient problem of destruction. It was not heroism as we usually understand it. It was something perhaps more American, the engineering of victory. The guns of the Meuse-Argonne fell silent at 11 a.m. on November 11, 1918. Their echo has never stopped.